Finding and describing the discontinuities of functions. During this lesson, we will describe types of functions that have discontinuities. We will learn the three types of discontinuities. And finally, we will learn how to identify discontinuities in functions. We will try to identify them verbally, algebraically, graphically, and by using a table. There are some functions that have limited or restricted domains, and some of the most commonly encountered are logarithmic functions, square root functions, rational functions, and piecewise functions. But for this lesson, we'll be concentrating mainly on the rational functions with a brief introduction to piecewise functions. There are three types of discontinuities or breaks in functions that would otherwise be continuous. There are infinite discontinuities, we have point discontinuities, and we also have jump discontinuities. This graph is an example of a jump discontinuity. It happens with piecewise functions. A piecewise function is where the function changes at certain input values. So all the way from negative infinity to x equals 2, the function is this line with a negative slope. But for greater than 2, it switches to this function at the right. So in order to go from one function to the other, the function jumps from 2 to greater than 2. It goes straight up 7 units, all the way from y equals negative 4 to y equals 3. But what we're mostly going to look at in this lesson are infinite discontinuities and point discontinuities. We'll start with infinite discontinuities. Infinite discontinuities can also be called vertical discontinuities or vertical asymptotes. We will find and describe these discontinuities or breaks verbally, graphically, algebraically, and by using a table. I will first verbally describe an infinite discontinuity. The graph starts on the left from infinity just below the x-axis and goes to the right very fast, very flat, almost like a slope of 0. As it crosses the y-axis, it starts turning down pretty sharply. The curve touches 1, negative 1 and turns even more sharply by nearly x equals 2, going almost straight down. On the right side of 2, there is a nearly vertical line coming from on high, but which turns sharply to the right after about x equals 3. The curve touches 3, 1 and curves even more to the right, nearly touching the x-axis and going almost flat all the way to the right of the coordinate plane. Without seeing a graph, did you understand much of what I just said? Probably not. Now we'll say the same thing as I did just now verbally, but this time looking at the graph. The graph starts on the left from infinity just below the x-axis and goes to the right very flat, almost like a slope of 0. As it crosses the y-axis, it starts turning down pretty sharply. The curve touches 1, negative 1 and turns down even more sharply, and by nearly x equals 2, going almost straight down. On the right side of 2, there is a nearly vertical line coming down from the top, but which turns sharply to the right after about x equals 3. The curve touches 3, 1 and curves even more to the right, nearly touching the x-axis and going almost flat all the way to the right of the coordinate plane. I hope you can see that verbally, without the picture of a graph, it's pretty hard to understand. The picture of a graph helps to make things a lot more understandable. But this is where we see the infinite discontinuity. It's shown here by the red vertical line segment at x equals 2. Do you see how the curves on either side approach but do not touch the vertical line segment at x equals 2? We also call this a vertical asymptote. Now we'll evaluate algebraically. The function is f of x equals 1 over x minus 2. The infinite discontinuity will come where this denominator equals 0. So if we set up the equation by setting the denominator equal to 0, we'll be able to figure this out. Solve for x by adding 2 to both sides of the equation. Negative 2 plus 2 cancel on the left side of the equation. We bring down what's left, so x equals 2. So that's going to be where our infinite discontinuity is found, at x equals 2, which can also be called a vertical asymptote. And this confirms what we have already seen in the graph earlier. Now using a table, we'll do this one on the TI-Nspire graphing calculator. This is the view with the new operating system that came out in May of this year, 2011. We go down to the graph icon, the second from the left at the bottom, press enter. Enter the function f of x equals 1 over x minus 2. Graph by pressing enter. We see the graph just as we did earlier. We'll go to the table view. Press the menu key. We see all the menu options. Go down to 2, view. Press enter. Scroll down to view table. Press enter. We see in the table that where x is 2, the output is described as this, undefined. So we describe the discontinuity verbally, graphically, algebraically, and finally numerically with the table, 4 different ways. In interval notation, we have x is greater than negative infinity and less than 2, and greater than 2 and less than infinity. This u connecting the two intervals is called a union. Now we'll look at this function, f of x equals x squared plus 2x over x. We'll first attempt to find discontinuities graphically. We enter the function into the calculator. Next we press enter to graph. By graphing, can we observe anything that looks like a break or discontinuity? No. So if we were to leave it here by using the graphing calculator, we would stop here and just say no. But we should be able to see that there is a discontinuity because we see this value x in the denominator. We should be able to figure out that what x has to be to make the function undefined. Let's say that we forgot everything. We'll come back to algebraically, so we'll take a look at a table view, a numeric approach. To get to the table view, we can just press Control, then T on our Nspire. We see that where x equals 0, the function is undefined. Now we'll go to algebraically. Let's simplify this function by factoring the numerator. X over x cancel each other. And so this is a removable discontinuity, also known as a point discontinuity, or we can call it a hole. And while it doesn't show up on the graphing calculator when graphing on graph paper, we represent the point discontinuity with this open circle point. It means that the function is not defined at that input value. In this case, the input value is 0. Now for a problem. What type of discontinuity may not show up when graphed using a graphing calculator? Stop the video, solve the problem, then restart the video to see how you did. The best answer is A, a point discontinuity, which can also be called a hole or a removable discontinuity. Next problem, which input value is excluded from the domain of the following function? We are given the function f of x equals 5 over x plus 4. And we're given 4 multiple choice answers. Stop the video, solve the problem, then restart the video to see if you got it right. The correct answer is C. When x is negative 4, that's because the value that makes the denominator 0, and therefore the function undefined at x equals negative 4. Also, when you graph it in a graphing calculator, this is what it looks like. We can see the vertical asymptote at x equals negative 4, shown by the red vertical line segment. Next problem, what is the domain in interval notation of the following function? We're given the function f of x equals x over 2x minus 18. Stop the video, solve the problem, then restart the video to see if you got it right. The correct answer is B. It's one of the 2 answers in interval notation in this problem. Here we see the vertical asymptote at 9, x equals 9. And here's the table view where the function is undefined at x equals 9, and it's greater than negative infinity on the left side and less than infinity on the right side. So B is the correct answer. Here's our last problem. What is the set of input values excluded from the domain of this function? The function is x squared plus 2x minus 15 over x squared minus 9x plus 18. One trinomial divided by another trinomial. Stop the video and solve the problem, then restart it to see if you got it right. The correct answer is A, 3 and 6. This is what it looks like graphed. We see a vertical asymptote to the right at about x equals 6. But the table view is what really gives it away. We see the function undefined at both x equals 3 and at x equals 6. We could also have factored the denominator and the numerator and evaluated using that information, solving x for 0. This has been finding and describing the discontinuities of functions. Thanks for viewing.